So what are our choices? Okay, so we'll make a little menu of choices and investigate the consequences of making the choices. One is we can so-called annul the instruction. So that's a term you see in pipelining literature a lot, the idea of annulling an instruction. That means turning the instruction into basically an instruction that has no effect on the state of the machine. So even though it says XOR, what we're going to do is say, never mind, we'll throw that instruction away and do nothing. We're going to execute a no operation. Okay. So, and we could, now there are different ways we can do that, and we'll have a very simple way that turns out to serve us well. You can turn off worth in the right, so, the things that cause the state of the machine to change, you can just basically disable them, and now the state of the machine doesn't change, so it's like the instruction was never executed. So annul the instruction and say, don't execute the XOR. Okay? Or we can program around it, right? We can basically put explicitly an instruction that does nothing, so you can go ahead and execute it. It's fine, processor, execute it. I know that you are going to execute it. I'm going to plan for you to execute it. And since I don't, I'm going to put in a no operation so that no op is, what is an example of a no op? It might be something like this. Add, R31 to R31 and stick the result in R31. Any instruction with a destination of R31 doesn't change anything in the machine, right? I mean, that write gets thrown away in the register file. So, I could follow all my branches by an instruction like that. Or, since the compiler knows that instruction will be executed, maybe the compiler can put an interesting instruction to be followed there, knowing that each loop actually has one last instruction it executes before it jumps back to the beginning. So the branch is not the last instruction at the bottom of each loop. It's actually the second to last instruction, and the compiler knows maybe I can figure something clever to put in that I really want to have executed if I'm going to continue the loop. So branch alternative 1, annul the instruction. So when I take the branch, what I'm going to do is simply replace that XOR as it moves from the instruction fetch. So I sort of know the branch decision right here. So as this instruction would have normally moved through into the instruction register for the execute stage, as it does that move, if I don't want to do it, I'll replace the instruction I fetched with one of these magic no-op instructions. Okay. So you can say, well, okay, that gets the job done. The thing to keep in mind is about 14% of the actual executed instructions, and this is the spec mark is a sort of famous set of benchmarks for measuring processor performance, is that about 14% of actual executed instructions are taken branches. So that means that if accounting for now the branch instruction, right, that means about 12% of the total cycles would be annulled. So that would mean that this particular solution, although it keeps the semantics correct, is pissing away 10 or 12% of the performance of your machine on the, sort of, if you went off and did a bunch of measurements, this is sort of what our benchmarks tell us you would measure. Okay, so you can say, well, my machine is running somewhat faster. On the other hand, I'm throwing away some of the extra performance by, getting some percentage of the instructions to work less well. So keep that in mind. That's alternative 1. And it's executed very simply in the hardware. If we choose to annul an instruction, if we say down here, we're doing the branch offset calculation, we're looking at the output of this NOR gate, we do want to change the program counter to actually jump to the branch destination. When we do that, we know we're no longer going to be executing the fetched instruction, because that's the instruction that we're going to throw away. We simply use a multiplexer and we put in a different binary representation of one of our no-ops in order to rewrite the instruction that we fetched into something that will have no effect on the state of the machine. So the hardware is not very complicated. It just has mostly a cost in performance. Okay, well, you say, well, SMOP, Chris, small matter of programming. Why, instead of adding hardware, why don't we tell the software guy to go off and simply put in no-ops? Well, now your programs are longer, So now all of a sudden you have all these no-ops filling up your memory. And so instead of synthesizing them in hardware where needed, we put them into the actual program itself. So a little less hardware, but the cost is my programs are now 12% longer than they were, which is, that's a non-trivial cost, particularly on, cell phones and watches and washing machines and things like that. These costs add up. Okay, so we could do the same thing in software, and now we're getting into the fanciful part. I'll take into account that, in fact, I'm going to move the add that was at the top of the loop. I'll do it once up here, but then each other time through the loop, I'll make that the instruction that will be executed after I do the branch. And so I'm thinking about this rewrite that I can, reorganizing of the instructions to put something useful that can be executed in the branch delay slot. That's what we call the instruction, okay, that comes after the branch is being fetched. And the instruction in the branch delay slot will actually execute it and tell the programmer, don't put in no ops, see if you can rewrite the program to put in something useful. And you say, okay, well, if you think about how this works, that would mean there's one extra add somewhere in here, and we have to add an instruction to undo the effect of that add. It's sort of a pain, and often you can't really do that, right? So the chances of rewriting the program this way get a little small. Yes?
On the previous slide, the branch enrollment hardware?
Yep.
Don't you have the same problem with setting that mux because you have information flowing backwards?
Well, what we're doing is we're making a decision in this stage about what to do with the instruction that's currently being fetched. And so long we can get the signal here with enough time to rewrite the instruction right before the end of the cycle, it'll work. Okay. Okay, so the final solution is to actually, instead of rewriting the program, is to do something here that we say, look, this program was written to execute this instruction when the branch was taken, but if you don't take the instruction, if you don't take the branch, annul this following instruction. So we can get more and more complicated about sort of trying to instruct the machines about when to execute the instruction in the branch delay slot and when not. The thing I should point out is that all these modifications, aside from the addition of the no-ops, all these modifications to the, whether to execute the instruction before or after the branch work well in a pipeline processor, but that means that the same program doesn't work in an unpipelined processor, which when it takes the branch simply isn't looking at the next instruction at all. So we're a little nervous about some of these alternatives because they actually, even though they make our pipeline processor work, the same program will not give the same results in an unpipelined processor. Okay, so in general, in our implementation of the pipeline beta, we're going to choose to keep the semantics of the programs the same between unpipelined and pipeline. So we're going to choose to do the annulment in hardware. So we'll add the little bit of hardware so we don't have to rewrite any programs, make them longer, and we'll take that small performance hit. So that's going to be our choice. So just to back up a little bit, here's our 5-stage pipeline. Notice that every time we take a branch, we have to throw away sort of the instructions in earlier stages because they relied on thinking that I'm going to continue execution, and the branch changes the execution order. So that means wherever the branch decision takes place, in the case of a B&E or something, we're making a decision on the information coming out of the register file, which means that we only have to throw away the IF instruction, the instruction in the IF stage. However, if we made our branch decision later, so for example, if we had a branch instruction that compared the output, the result, used the ALU to do a subtract and find out if one register was greater than another, and we made a branch, we could say branch register A greater than register B, if that was an instruction in our machine. If we chose to take that branch, we'd now have 2 instructions to throw away. And if we had a sort of a branch of memory 0, we could test the results coming back from memory, okay, we'd have lots of instructions to throw away. So this notion of a branch delay slot and throwing it away, these start getting more and more and more expensive. Okay, the later the branch decision gets made, the more instructions that follow the branch are in the pipeline and have to be flushed or thrown away or annulled, okay, if the branch changes the order of execution. And in fact, a lot of the hardware that you buy is devoted to very clever solutions. Okay, it says, well, I don't know, I'll sort of think of, I'll speculatively have two programs running now, one of which has that instruction executed and one of which doesn't, and I'll sort of keep track of sort of several generations of speculation about what's actually happening in your program, and when I finally make the decision about which is the right speculative execution, I'll throw away the old execution. So one way to use a lot of extra functional units is to have them guessing about, did I want to do that XOR or not? And one branch will assume I did, and the other branch I assume I don't. And when I finally make the branch decision, I can choose which execution branch to do. Okay, so speculative execution is something that your processors try to do very well, but they end up throwing away some percentage of their work because they've invested in executing multiple paths to your program, only one of which will be the true path once the decisions get made.